Okay, I think we are live. So welcome everyone to the Latin American webinars on physics. We are today on our edition number 172. We are super happy to have Kuldeep Deka from NYU Abu Dhabi. So Kuldeep got his PhD last year in the University of Delhi in India. And since then he joined NYU Abu Dhabi as a postdoc. And today Kuldeep will talk about heavy neutral leptons without prejudice. So let's see what he has to tell us. So welcome, Kuldeep. We're happy to have you.
Yes, thanks a lot for the invitation. And yeah, I'm very happy to be presenting here. Okay, I'll share my screen.
Yeah, please.
It's visible, right? And my sound is also
Perfect.
clear, right? Yeah.
Yeah.
Okay. So, so today I'll be talking about this topic, heavy neutral leptons without prejudice. So this is based on a work which has already been published, and another one which is in the process and which will be coming out very soon, hopefully this month. So so without further ado, I'll start. So so we all know that in 2012 the Higgs boson was discovered, and it confirmed the mass generation via Higgs mechanism, and more or less the particles within the standard model were kind of completed. And so this is a depiction of the Higgs mass, which from Atlas, the peak at 125 zeV. So but there were certain shortcomings which the standard model couldn't address or cannot address as if now, and some of these are like the neutrino mass, dark matter and matter antimatter asymmetry, and also some other issues, some related to more theoretical aspects, and also some other experimental anomalies. But since I'll be talking about heavy neutral leptons, so that's why I highlighted only these three. Now about neutrino mass, we all know from neutrino oscillation experiments that I mean, a neutrino has tiny mass in the EV scale range, and at least two of them has to have mass in order to satisfy the oscillation data. Similarly, from various galaxy rotation curves, or bullet cluster CMB observations, we know that there is dark matter which cannot be explained by the standard model particles, and then there is this matter antimatter asymmetry, the axis of matter over antimatter. So and this is where these HNLs come into the picture in terms of their motivation. So these are of course BSM particles, beyond standard model fermionic particles, and it's an addition of three flavor paradigm and can couple to all the standard model neutrinos through a Yukawa kind of an interaction. And they can be both Majorana or Dirac. And if they're like, say, maybe scalar or higher, there is no oscillation with the standard model neutrinos because of the small coherent length. So the HNLs could explain the neutrino mass through seesaw mechanisms. It can satisfy the matter-antimatter asymmetry through, I mean, CP violating effects. Say if the HNL decays to neutrino and antineutrino with different rates. So the CP and CP conjugate process have different rates, then it can lead to leptogenesis, which can then further be converted to baryon asymmetry through Spelleran processes. Then it can these HNLs can also act as dark matter candidates if they have around keV scale mass, which are stable in cosmological scales. But yeah, I'll not be talking about these aspects. I'll be talking about their probe at colliders mainly. So so once we have, since I already mentioned this interaction here, so once the Higgs get a vacuum expectation value, we get Dirac masses like this, and which is like proportional to the Yukawa. If the setup has more say channels or additional scalars, there could be other Dirac masses, and once we have the full mass matrix and we diagonalize it, the light neutrino flavor states can be written in this form. which makes the HNL, which is represented by capital N, inherit couplings to the standard model gauge bosons, which we denote by phi, or it's also known as mixing. Now, so usually when we talk about these mixings and Yukawas, so they are typically related. So for example, in the type 1 seesaw, it has a very linear kind of a relation, which the mixing is proportional to the Yukawa times the vacuum expectation value of the Higgs over the mass of the heavy neutral lepton. For the scottogenic case, where the neutrino masses are generated via loops, so the Yukawa could be 0, but we still have a non-zero mixing parameter. In the inverse seesaw case, it's similar to type 1 seesaw, except that there is an additional scale mu, which comes into the picture, and it's so the relation is slightly different from the type 1 seesaw. There are other cases like double seesaw and some other as well, which I'm not going to mention here. Then there could be cases where this mixing could be exactly 0. So here I'm just pointing out one example where if we have Dirac HNLs, two pairs of Dirac HNLs where one is say light and the other is heavy, along with some additional scalars, and we introduce some other discrete symmetries or even continuous symmetries. And if we have this form of a setup, then we can show that once we diagonalize the mass matrix, we can have a scenario where the Yukawas, which is represented by Y and Z here, are non-zero, but the mixing is exactly 0 to NR. Okay. And yeah, these are the two references where like this kind of setup has been discussed. So if I summarize it, like this relation between the mixing and the Yukawa is highly model dependent, and but we usually just emphasize on the mixings when we represent the parameter space from experiments. So and yeah, that's the thing. So collider constraints, or in general any constraints for HNLs, are usually shown in this V square Raman plane. And these are some of the regimes where or different mass ranges where they have been probed. So it's like below K1 mass, so here, then below B meson or D meson masses, and then below say W or Z decays, and then above the vector boson masses, we look at vector boson scattering. And so there has been various experiments which has looked into it, and so along with these mass regions, there is also this long-lived displaced and prompt region, which I'll be coming very shortly. And okay, so these are the current status in terms of the exclusion bounds from the experiments. So here this region is for long-lived particles. Then we have the displaced region, and then like the prompt region. So, and these are the masses represented by this like the K meson, the B meson, and the Z boson. So this is when the heavy neutral lepton couples to the muon flavor neutrino or muon mu lepton. Similarly, for the electron and the tau flavor, these are the limits. For the electron and muons, the constraints are more stringent compared with respect to the tau. Okay, so this is like the current status of these HNLs as far as when we represent the constraints in terms of mixing versus the mass. So now we ask this question: what we give up these model prejudices, which typically assumes a relation between the mixing parameter and the Yukawa. We give up that prejudice and treat both the mixing and Yukawa as free parameters. And to the first approximation, we treat the mixing to be 0, and we just focus on the Yukawa. And as a result, we just have to look at the Higgs decays. So decays, the HNLs produced from the Higgs, because the mixing parameter is 0. So the gauge bosons, the standard model gauge bosons doesn't enter into the picture. And so we can utilize the Higgs constraints like the total decay weight or the invisible decay weight, etc., to constrain these scenarios. So in the setup, we will be using the factor boson topology of the Higgs, which is represented by this diagram, to use it to reduce our backgrounds. And so in yeah, and then the heavy neutral lepton will decay to will have a three-body decay to a neutrino and then off-cell Higgs, and the off-cell Higgs will finally decay to fermions, standard model fermions. Okay, so it's the same information. So basically, this is the decay weight of the partial decay weight of the Higgs going to an HNL, and then the HNL going to three-body final states, since the fermions which connects the off-cell Higgs is will have this Yukawa, which will be proportional to the mass of that fermion. And so this y square versus mass displane can be divided into three regions in terms of the decay length, or C tau, which is the inverse of the decay weight, total decay weight of the HNL. And so there is this region which is larger than 480 meter. 480 meter is coming from like the far detectors which are proposed at the LHC. So this particular region is LHC stable, so they will never decay inside the LHC detectors. Then below 480 meter, we have this region where we can have long-lived signatures if the decay length is high, or it's between 1 meter and 480 meter. If it is less than 1 meter, but more than 1 millimeter, we have the displaced regime, and more than and less than 1 millimeter is the prompt regime. So it's shown here. So yeah, so this region is the LHC stable. Then this is for the far detectors like FASER and MATHUSLA. Then we have the displaced vertex regime, and then the prompt regime. So in order to do our analysis, before going there, so here are the branching ratios, and since these HNLs will decay through an off-cell Higgs, and the Higgs will couple to two standard model fermions, so it's evident that the BB bar will have the highest branching ratio once that channel opens. Once we cross the BB bar threshold, this is the most dominating one. Below the BB bar threshold, it's either the charm or the taus, which are the dominant, and we have some branching towards muons if we are towards very low mass region, or where below 1 GeV, when these charm or taus and BB and Bs they do not open. So okay. Now for the prompt case, and since okay, so for the prompt case, we'll be only concentrating on the HNL decaying to two BZs along with a light neutrino. So in order to separate the signal from the background, we use the vector boson fusion selection criteria, which was depicted in this diagram. So here we have two forward jets, which are most likely to be in opposite hemispheres with a large pseudo rapidity separation and a large invariant mass. So this helps a lot in reducing the background, and also they're supposed to be highly energetic with high PT. So we use those selection criteria to select the signal events, and along with say the mass of the BB bar, which should be close to the HNL mass. So those constraints, those variables, along with missing energy, because we have two neutrinos in our final state. So this helps us reduce the background, and in order to reach a 3 sigma sensitivity. So this is the current constraint which we have for the prompt case, for a 14 TeV center of mass energy and 3000 femtobarn inverse luminosity. So this was the prompt case. Now, if we talk about the displaced case, so we maintain the same factor fusion selection criteria, but now we demand so we let go of the requirement of bz's, and we look for any z's which has a displacement of this 1 millimeter and 1 meter for dxy, and dz to be less than 300 millimeter. And so this is the exclusion region which we found, which we find out. So this thick black line corresponds to a scenario where we have no background events at all, and if we have say background, if we have background events which is set to 65, since so the number 65 is derived from the fact that if we are at the current luminosity at the LHC, and if we say see 3 background events, then we scale it up to the luminosity of 3000 femtobarn inverse, and we get a total of 65 events. And in that pessimistic scenario, this thin line is the this thin line represents the exclusion bound for the displaced case. Then if we talk about the long-lived case, then so here I show the like the detector specifications for the phasor 2, where we have a radius of 1 meter and radius of 1 meter and and the length of 10 meter for the detector, and the probability of decaying inside the detector is given by this expression. And similarly, we also do a similar analysis for MATHUSLA, which yeah, so and this is the sensitivity reach which we get for FASER and MATHUSLA. And the thick black line is the combined sensitivity to all the channels. And if we talk about individual channels, so then these are represented by these lines inside. Okay, so I think one thing I forgot to mention here was, okay, so this shaded region, so this particular region is given by the total decay width of the Higgs, and this region is given by the invisible decay width of the Higgs. And the invisible decay width only comes into the picture when the HNL doesn't decay inside the detector, and it escapes the detectors, because we don't have any other sources of invisible branching for the Higgs as far as this setup is concerned. So it only is present in the long-lived regime and not in the displaced and prompt. So, and these dotted lines are the future sensitivity which high luminosity LHC can reach in future. Okay, so if we combine all these 3 regions, the prompt, the displaced, and the long-lived regime, so this is the final exclusion which we get in this y-square versus mass blend, and in this simplified scenario where we assume that the mixing is exactly 0. Okay, so this was the first part. Now, what if like we allow both the Yukawa and mixing, which we assume to be free parameters, as I had already mentioned. We allow both of them to float and see like how it behaves in this phi square versus y square plane. So this is just a plot to represent the branching of a Z to an HNL or a Higgs to HNL for different branching ratios, different values of branching. Of course, like 1% is the more physical one. These are not physical if we compare to experimental data, but just for depiction we show this. So we see that in order to satisfy this 1% branching, the Yukawa has to be very small, whereas the mixing can be large. So but then this implies that if we want to satisfy this 1%, but the production will suffer if it is produced only through the Yukawa. So anyway, we move ahead, and so as we had plotted for the previous case, y square versus m, the 3 different regimes of the long-lived, displaced, and prompt decay. So we can do a same in this plane, phi square versus y square plane, when the HNL when the HNL can decay through both decay through off-cell gas bosons as well as the Higgs. And so this is where it's so for 10 and 20 GeV it's more clear. So this region is the LHC stable region. Then we have this region between 480 meter and 1 meter where we have the long-lived regime, And then between 1 meter and 1 millimeter, we have this displaced regime. And then finally, below 1 millimeter, we have the prompt regime. These are not very not all of these regions are can be seen for 2 and 5 GeV masses, because the masses are low. So that's why we need larger couplings to get the same decay length. But as we go towards larger and larger masses, the decay width increases because it's proportional to the mass to the power 5, and hence we can probe lower and lower couplings for even the prompt case. Okay. So yeah, precisely the same point is being shown here, where this is the LHC stable region, then we have the phasor, and then the displaced regime, and finally the prompt regime. Okay. So now if we do the actual analysis, and so we stay in the scenario where the HNL is still produced through the Higgs, because of course we are putting VBF vector boson fusion selection criteria, so that it ensures that it's produced through the Higgs. But now we also have the mixing, so the decay could happen both through the mixing and Yukawa. So for the prompt case, where I have shown two benchmarks, say a mass of 45 GeV and a 70 GeV. So since the production is happening to the Yukawa, we need a particular value of Yukawa so that we have sufficient statistics to get a 3 sigma significance. But as we increase the mixing, which is given by this y-axis, so at some point there will be a point when the decay will happen both through the mixing and the Yukawa, and this is this slight change in slope here. And finally, once the mixing is large, so the entire decay will happen through the mixing. But since we are also looking at, say, BB bar final state, and for Yukawa, the BB bar one was the largest one. But if we go towards mixing, so the decay which are more democratic for all the fermions, because there is no dependence on the mass of the fermion, and as a result, the decay which slightly decreases, because of which we need a larger Yukawa here to maintain the same 3 sigma significance or the same statistics. And so this is how it goes, like for both 45 and 70 GeV. These two are the displaced case, where again it follows, so the shape of this these two curves, where again, like, this thick black line is for no background, and for this thin black line is with backgrounds, the same as I had mentioned, the 65 background events. And if it will always follow this kind of a region where the displaced vertices are like kind of where we can have displaced vertices, but it cannot go towards very small values of Yukawa, because the production of the HNL will suffer. So we have this kind of a shape. For the long-lived case now, since we are assuming that there are no backgrounds, because we can always use the we can always use this large decay length to filter out any backgrounds, and so we focus on the decays happening from the channel production happening from both from Higgs as well as the gauge bosons, and these are the individual rates. And if we combine everything, so this thick black line is what we get. So this is for 2 GeV, then 5 GeV, 10 GeV, and 20 GeV. For like, we also show the type 1 line for reference for these masses, for these individual masses. Now, okay, so this was the case for LHC, where now we have both the Yukawa and mixing. But at least for the prompt case and the displaced case, the production is happening through the VBF Higgs decays. Okay, so now this is what we have for the Higgs, but we also wanted to see how the prospects look at the FCC, because FCC is being promoted as a Higgs factory, as well as it's a like 10 to the power 12 G's will be produced. And also for the Z Higgs production mode we will have like at least 10 to the power 6 Higgses. So we wanted to see how this sensitivity fares in comparison to the high luminosity LHC. So we used the Z-pole. We did the analysis at Z-pole as well as the Z Higgs production mode at 240 GeV. So here are the results. So if we just consider that the mixing is 0 and we only have the Yukawa, so this is the sensitivity reached for the Z Higgs production mode at 240 GeV, which is given by this this column and here in terms of luminosity and mass, or the square root of energy, sorry. So it is supposed to, so it is expected to reach a luminosity of a total integrated luminosity of 7.2 attobarn inverse and square root of energy of again 240 GeV. So this is the sensitivity reach, which is given by the blue line, whereas the black line is what we get for the HLLHC. So we see that we don't gain much. And as far as if we combine FCC, HLLHC, and other future colliders, this is the sensitivity in the Higgs total decay width measurement, which is given by this line, the lower dotted line, which is almost being overlapped with our sensitivity reach. So in these colliders, if we combine everything, we can hope to reach these limits what we have for our case. And similarly for the displaced case as well, we see that the HLLHC fares marginally better compared to the FCC-ee. Now if we also allow the mixing parameter to float, and we look at this general case where this both mixing and Yukawa are free parameters. So this is what we get for the Z pole. So now again for the Z pole, the production will only happen through Z decays, but the decay can happen through both Yukawa and mixing. So again, so that's why we get a fixed value of mixing parameter, so that we get sufficient statistics to maintain its sigma significance over the background. And then at some point, as we go towards larger and larger Yukawa, there will be a so the Yukawa will come into the picture. And again, because of the similar region of branching ratio being different when the decay is dominated by Yukawa versus when it's dominated by mixing, we will have a dip of this sort. But we see that the relevant region where this Yukawa actually enters into the picture is already excluded by either the current limits on the mixing parameter or the limits on the decay width of the total decay width of the Higgs, which is this shaded region here. Now, and so these two are the prompt for 45 and 70 as earlier. If we look at the displaced case for these four masses, 2, 5, 10, and 20, so this is the reach, and again it follows the same pattern for displaced vertices, which is like this rectangular, so inverse rectangular hyperbola kind of a function. But here now since the production is being is happening only to the Z, so we cannot go towards very small values of V because it will affect the production. And these three different lines are for 100, 10, and 1 event, which finally survives this selection criteria. For the Z Higgs production at 240 GeV, we now we can have production both through the Higgs as well as Z, and this is how it looks like. So for the prompt case, and then for the displaced case, we actually have two different we segregate this to VE square versus V mu square plus V tau square, because for the electron channel we have an additional contribution coming from a T channel W exchange, which doesn't happen for muons and taus. So this is for that electron channel, and then for muons and taus, this is the combined reach which we get for Z Higgs at 240 GeV. Okay. So we also tried to see if we can utilize the previous analysis which was done by various experiments. So for example, if we go back to this current exclusion. Let's take the muon flavor. So here we picked out the most stringent limits. For example, for the muon channel, this nu TEF is the one for below, say, around 1 GeV HNL mass. Then then between, say, 1 GeV and 10, we have this limit coming from CMS. And as well as for higher masses larger than 10, we have this CMS limit here, which are the stringent. So we tried to see if we use these limits on the mixing, and if we can try to recast it in terms of the Yukawa versus mixing, the scenario which we are proposing, where this mixing and Yukawa are both free parameters. So this was the I wanted to mention something here. So we also use the Delphi result, because Delphi looked at Z's, and since our final state, so if we just look at the Higgs, and if the off-cell Higgs decays to a BB bar, that's where we are more sensitive to, because of the large mass of the B quark. So that's why we also wanted to look at the Delphi. And this is what we found out, that for Delphi, like if we look at the mixing versus Yukawa, the Yukawa doesn't have any effect, even if we increase the even if we look at very large values. However, for other experiments, like for 1 GeV HNL, we have the nu TEF, which is the most stringent. Then for 10 GeV, we have CMS. We have a limit coming from CMS. Similarly, for 30 and 60 GeV, these are 3 different analyses. Especially so for the 10 GeV, it's a different analysis. For 30 and 60, we have it's a different analysis. So in all of this, we see that around the Yukawa y square value of 10 to the power minus 2 or y of 10 to the power minus 1, this starts to show some change of slope, and this is where the Yukawa will enter into the picture. But these limits are not very interesting from that point of view. So this was the entire work which we did in this respect, and so finally I'd like to conclude and open the stage for questions. So again, it's heavy neutron leptons are very interesting in terms of, say, neutrino mass, dark matter antimatter asymmetry. The relation between Yukawa coupling and mixing are highly model dependent, although we always tend to just focus on the mixing, and since they are dependent, we can always we always float this idea that we can express one in terms of the other. It's a one-to-one translation. Then, but if we just focus on model independent sources and treat this Yukawa and mixing as independent parameters, then we can get this complementary approach, where we can utilize the Higgs decays, and we can look at the prompt signatures, displaced vertices, as well as long-lived particles. Sorry, was a typo. Particles. The FCC reaches were also presented, and it was not. I mean, it was competitive with when we compare it with high luminosity LHC. And Higgs sector has to be further tested, so that the Higgs parameters can put constraints on this kind of scenarios. So with that, I will just thank you. Thanks a lot.
Excellent. Thank you very much, Kuldeep. Very nice talk. So are there questions or comments from the audience? Well, yes.
I have questions. The first one, I think I know the answer, but still, so at some point, you put bounds on the branching ratio of Higgs going to invisibles, but
Yes,
on your model without mixing, that shouldn't happen. I mean, the Higgs will always go into a light and the heavy. So how do you put that bound?
So yeah, so that invisible will only come if the HNL escapes the detector.
Right. Okay.
Yeah,
That's what
only
I
so
mean.
that's why it is only relevant in this region where it's the long-lived regime.
Oh, that's
Yes.
where it is. Oh,
Yes,
sorry,
yes.
I hadn't noticed.
Yeah, so let me go. I think there is a different plot where this can be emphasized better. Yes, so if you look here, so you see, like,
Right. Yes. Okay.
this is the boundary for the long-lived regime, right? Like from here on, it's the long-lived. So only here that bound applies, not on the entire
Sure.
parameter. Yeah.
Fantastic. Fantastic.
Yeah.
Okay. So now what I really wanted to know is what did you impose on the vector boson fusion for triggering the analysis? That's crucial, right? Being able to trigger on
Yes.
the surge
I
using
mean,
vector boson fusion.
yes. So yeah, I mean, there could be two different ways, I think, which can be done. First of all, you have these two forward jets, right? Let me
Yeah.
go to the selection criteria once. I think I have it in my backup slide. Just give me 1 second. Yeah, so these were the selection cuts for the prompt case. So we have, so first of all, we don't want any leptons or photons because it's not present. Then we have at least two non-beta jets or the two forward jets, which are highly energetic. And so we can always, trigger on them to look into this. Along with this, and of course, those two jets will have high PT. So we set a PT requirement of 60 and 40, and also an HT of 140. And the other aspect of these two forward jets is that they are in the opposite hemisphere because they are forward jets, right? So they also have a large pseudo rapidity separation and also a large invariant mass. So these two jets could help in triggering. Along with this, since we also have, say, a missing ET, like two sources of missing energy, right? One coming from the HNL, one coming from the neutrino, which is connected to the Higgs when the HNL is produced, and the other neutrino when the HNL decays. So this can also, we can also even trigger on the missing ET, but of course, this is, I think, not very currently, like how the current is missing ET triggers are designed. I think it's not very efficient right now, but maybe in future, yeah. So
yeah, because the triggers with missing ETs are like 200 GV or something, and
yes.
For things coming from the Higgs, I don't think that's very yeah. But okay.
But the two forward jets could always help you. Yeah, this could always help you.
Okay, great. And how are you doing the detector simulation?
So yeah, so what we did was we just used Delphi's question, and of course we used we used the efficiencies for this B tagging and even other things. Those are the typical ones which we usually do even for LHC. Like, so we use the same cards, and yeah, but yeah, we use Delphi's for this.
Right, and then you included an acceptance due to, for instance, for the far detectors, you added an acceptance due to the fact that not all particles are being detected.
No, I think for the far detectors, the only probably the only thing which we had was the decay length and nothing else, probably, because I think we didn't simulate that particular thing in Delphi's, but for the displaced and the prompt, we did it like in Delphi's, because again, like yeah, so it was only the decay length which was coming into the picture for the far detectors.
Right, but did you, for example, for instance, when one thinks usually about particles coming from Higgs decays, one wouldn't assume that they go very much in the forward direction, right? So if you are using FASER, then you have to take into account
Yes.
that.
So yeah, yes.
So I don't know if
Sorry,
you took that into account. Yeah.
Yeah. So yeah. I mean, we took, so we did select particles in the region where, like, say, this three-dimensional space where this detector is located. So yeah, we did put those cuts on the phi as eta. So those cuts were there. Along with that, the decay length. Yeah. Sorry. Yeah. I forgot to mention. Yeah.
Okay. Super.
Yeah.
Okay.
So the spatial resolution was taken, and then along with it, the decay length. Yeah. So
Nicolas is telling me on the chat that I should shut up because there are questions on the chat. So
that's not true. Okay, it's true that there are questions in the chat. Okay, so our dear Arseni is asking about GGF. So his exact question is, at the LHC, the dominant production mechanism for the Higgs is gluon-gluon fusion. You focus
Yes.
on VBF. Did you consider gluon-gluon fission as well? It should improve the limits.
Yes, it should improve the limits, but then we also wanted something to trigger on because, and for that we had the two forward jets, which is not there for the gluon-gluon fusion. And as I had already mentioned just now, that the missing ET, I mean, okay, so missing ET could be one trigger, but then currently it's not very, I mean, as far as the current triggers are concerned, it's not very efficient probably. So yeah. But then again, we had also, if we consider the gluon-gluon fusion, then we couldn't use the VBF topology to our advantage to, reduce the backgrounds probably. So I don't know how much efficiency it would have improved. But so when we consider the VBF topology, there is always a non-trivial probability that some of the, the initial gluons could radiate some jets, and then they can contribute to this topology. We did take that into our picture. But yeah, we always focused on the VBF topology.
Good, thanks. Are there further questions?
Yeah, one
Comments?
comment is that, of course, yeah,
Please,
you can
please.
also the Higgs-Strahlung, right? Where the Higgs is producing a station with a V or a W. But I don't know what's the impact on the because applying vector boson fusion is complicated, right? There's a lot of things that need to be taken into account.
Yes. Yes.
But in principle, the claim is that the background is very much under control. The other ones like Higgs-Strahlung are like half an order of magnitude below, 1 order of magnitude below vector boson fusion. But
Yeah.
in principle, you just have to trigger with one lepton and that's it.
Yeah.
But I don't know what the impact on the background is in that case.
Yes. Yeah.
You have to be very careful with the posterior cuts. But for triggering, maybe it's easier with the other one. What I don't know is the background.
Okay. Yeah. Could be looked into. Yeah.
Okay, Arsen is very active in the chat. He said that he agrees, but he still thinks that taking GGF into account should improve the limits.
Okay. Yeah, I mean, yes.
Roberto, you had some question, maybe? No?
Yeah, but I was thinking in the scenario in which you have a light fermion, I mean a light N fermion and long lived. Is it possible that could mess up a little bit cosmology bounds like BPN or something like that? If it is long lived enough to mess up, I don't know. I mean, if you have comment on that, because it's completely kind of off topic of your talk.
Yes, I think, yeah, so there are already limits on the mixing versus mass as from cosmology. So if you look at this, say, this is same for all the flavors. So if you look at these masses versus mixing, so this dashed line, so this is what we already have from cosmology, and there, yeah, you could, violate some of these cosmological bounds, yes.
Okay, thank you.
I think the point here, just to complement what you say, Kuldeep, is that what Kuldeep is calling like long-lived is nothing. I mean, for colliders it's a lot because it's hundreds of meters, but for cosmology it's prompt, right?
Yes, sorry, yeah. For cosmology it's prompt. For colliders, say 1 kilometer or for 500 meters, that's what I'm talking about when I say long-lived. Yeah. And that's why, like, if you see, like, these limits are more towards lower masses and also towards very low couplings. So only then it could be, it could mess up cosmological observations. Yeah. So, but I am in this kind of a regime, which is, I think, still safe.
Further questions or
About
comments? Yeah.
another question, because I remember, I mean, this setup may be similar to a setup that I remember that they were studying about the near detector in June or part detector in June, in which they they modify the unitarity between neutrinos because there is a four neutrino-like fermion that it mixes with the neutrinos, let's say, but heavier with a different mass.
Mm.
And I don't remember. I mean, I guess they can establish some kind of not limit, but forecasts to be observed in June. I mean, it doesn't need to be as high as GeV, but in the range in which it's still cosmology compatible. It was a work from Valentina de Romeri and other people. No, Valle and Omar Miranda. I remember those papers. I mean, it's kind of a complementary study because they are assuming just that you have a non-unitarity neutrino sector, and what would be the role of this non-unitarity in the event count for June. But I thought about that. It's not a question, it's just a comment.
Yeah. Mhm.
Good. Anything else? I don't see more questions in the chat. So I think that's it. Thank you very much, Kuldeep. It was
Yeah,
clear.
thanks a lot for having me. Yeah.
No, our pleasure. And I think we resume in 2 weeks. No, we have our next webinar. So hope to see you guys soon. And thanks again.
Yes, bye.
Bye. Thanks.